Welcome to App Chemistry at Honeyniga High School. Today we'll be looking at Chapter 10, which deals with gases. On the AP test every year, about 5 of the 75 questions deal with gas ideas. And on the FRQ, somewhere in one of the FRQ questions, there's typically a question related to gases. Now, this is the first chapter of a two-part chapter test. So we're going to be looking at 10 gases and 11, which would be solids and liquids and intermolecular forces together is one test. And this will be the last multiple chapter test that we take of the year. Now, first section gets into characteristic properties of gases. Unlike liquids and solids, gases will expand to fill their container. They're highly compressible substances. They're always homogeneous with other gases, which means when you have a mixture of gases, after a very short period of time, they will be evenly and uniformly mixed. They only occupy a small fraction of the actual volume of the container. So gases don't take the volume of the particles, they take the volume of the container, unlike liquids and solids. And because they have a small amount spread out over a large area, they're going to have extremely low densities. So all of these would be properties of gases that would really differentiate them from liquids and solids. Now the next section gets into pressure. So 10.2 deals with pressure. Now pressure is the amount of force applied to an area. So if you're pushing on a wall, the force that you are pushing with compared to the area that you're pushing. So if you're pushing against the wall, that would be the surface area of your hand. So the force with which you're pushing divided by the area that force is being spread out over would equal pressure. So pressure is a force per area calculation. Now, if you're taking a look at air pressure, you need to understand that, pressure is caused by collisions. That's something we drove home in pre-AP chemistry. But you need to understand that those collisions are affected by all of the particles stacked on top of your head. So if you stack, 20 books on top of somebody, it makes sense that there's more books. They're going to be pushing down harder. It's a greater weight that's pushing down. So gases are a little bit trickier because you don't see them. So you need to understand that the same thing is true. When you're looking at air pressure, the pressure around you, it's really the gravitational force that's exerted on the entire column of air that is pushing down on you. So if you take a look at this is a meter squared column, so a meter by meter area, and that goes all the way up to the upper atmosphere. That entire column of gases is really stacked on top of that 1 meter square area. And the pressure those gases exerted aren't just the pressure exerted by the particles nearby hitting that area, but also the particles above them that are stacked on top that are being pulled down by gravity. So in terms of the force, remember force is mass times area. So the larger your mass, the greater the pressure will be. And the A in F equals ma would be the acceleration. And typically here we're looking at the acceleration due to gravity. So the force that gravity exerts on a massive object. That's how we would calculate that force. So obviously on Earth, the acceleration due to gravity is going to be relatively constant. So really all that changes is the mass. Um, on top of you. Well, in the case of air, you need to look at that entire column of air all the way up to the upper atmosphere. And remember, atmospheric pressure is the weight of air, or the weight that air is exerting on you per unit area. Now, units of pressure. The SI unit would be the Pascal. Now, a Pascal is an abbreviation for what it actually stands for, which is a Newton meter squared. And remember, a Newton, which is a unit of force, is an abbreviation. So remember, Newton comes from other things. Remember, force equals MA. So if we're talking SI units, the mass, that would be kilogram, and the acceleration would be meters per second squared. So that's really what a Newton is, a kilogram meter per second squared, and that's going to be over a meter squared. That's what a Pascal equals. So why do we call it a Pascal? Because a Pascal is a whole lot easier than that thing is. Another pressure that you will sometimes see, and this is relatively rare, is the bar. And a bar actually equals 10 to the fifth pascals, which is 100 kPa. So a bar is basically 100 kPa. And since normal atmospheric pressure is actually around 100 kPa, 101.325, So, I mean, 1 bar would represent about atmospheric pressure. It's not exactly true, but it's at least close to that. Now, other types of units of pressure would be things like millimeters of mercury or torr, and those two things are interchangeable. A torr is a millimeter of mercury. Well, how can a length be a pressure? Well, it's the length of a column of mercury. So what we're really looking at here is a length of a certain diameter of mercury, and literally then we're measuring the difference between the millimeters of height between our two areas. So what we have here is an example of a barometer. So the reason why we get millimeters of mercury becoming a viable pressure is because of barometers and manometers. What we have here is a tube that's been evacuated. When we put that evacuated tube in our pool of mercury, atmospheric pressure is pushing down on top of the mercury here, but there's nothing pushing down there. So literally, atmospheric pressure forces mercury up the tube. Now, the greater the atmospheric pressure, the higher it's going to force it up the tube. And this is counterbalanced. This height of mercury is counterbalanced by gravity. So that's why we don't get to the top of the tube. Eventually, we have a height of mercury here that is literally gravity is pulling down on it, and that prevents it from going all the way to the top. So what we're measuring here is literally a height of mercury. So that's how millimeters of mercury can end up becoming a pressure. So the pressure that this column of mercury exerts would equal the atmospheric pressure between the two. So a height of mercury in this particular case would be equaling to atmospheric pressure. Now, if we have a manometer, a situation we'll look at later, the same kind of thing can happen. We have two gases pushing differently on a column of mercury, and the difference in the height would be the actual difference in pressure between the two. So millimeters of mercury is another unit of pressure, and a torr is the exact same thing as a millimeter of mercury. Now, atmosphere is our last one, and this is a really, really common one. So we typically see kilopascals and atmospheres. Those are our most two common units. 1 atm, so normal atmospheric pressure, is about 760 torr, which is about 760 millimeters of mercury, which is around 101.325 kPa. Now, open-ended U-tube manometers. Now, you need to understand that one of the ways in which we measure pressures of gases is using what are called manometers. Now, a barometer is one type of pressure measurement. That's going to measure atmospheric pressure. If we want to measure the pressure of any gas, we can hook the gas up to a U-tube. So basically, we have a U-shaped tube with mercury in it. So it's going to be filled with mercury inside there. Now, if the two gases pushing down are equal to each other, then the heights of the mercury inside our U-shaped tube would be equal. Now, there's two different types of manometers. There's the open end and the closed end. Pay close attention to them because what the height actually means in terms of a pressure is different in both cases. Now, if we have an open-ended manometer like in this case, the pressure of the gas is going to equal our height plus the pressure that atmospheric pressure is pushing down. So we have to add both of these together. So in this particular case, the gas is pushing up a column of mercury, and that takes pressure to do that. And it's also fighting against atmospheric pressure because it's an open-ended manometer. So the pressure of the gas inside here would be the pressure of the atmosphere in millimeters of mercury plus the pressure of or the pressure related to the height of the mercury in millimeters of mercury. So this is one way of measuring the pressure of a gas, is using an open-ended manometer. Well, if we have an open-ended manometer, then we can also have a closed-ended manometer. The difference between the two is in this case, it's kind of like in our barometer. This is going to be a vacuum up here, so there is no pressure pushing down before, because this is a vacuum. So before we had atmospheric pressure pushing down, this case we have a vacuum, an empty area of space. So the actual height of the mercury is the actual pressure of the gas. So There's open-ended manometers and closed-ended manometers. And the difference between the two is very, very, very important in terms of understanding what the pressure of the gas is. So this is something you're going to have to be aware of and be able to do calculations. So if it talks about a closed-ended or an open-ended manometer, pay very close attention because you calculate your pressure slightly different between the two. Now, standard pressure, which is normal atmospheric pressure is sea level, would equal 1 atm or 760 millimeters of mercury, which is 760 torr, which is 101.325 kPa. So to a bunch of significant digits, that's what we've got in kPa. So this is a 6 significant digit number here. These both would be considered exact numbers. So they're an unlimited number of significant digits. So standard pressure is 1 atm, which is 760 milliliters of mercury, which is 101.325 kPa. Now, the next section past just talking about pressure, the next section gets into gas laws, and you should remember most of these from last year. So you're going to see a review of a lot of different things you had from pre-AP. Now, first we're going to look at the relationship between pressure and volume, and you actually did this last year in a lab, so this whole concept should be familiar to you. Now, if we plot the volume of a gas versus its pressure. So we measure the pressure of a gas and then measure resulting pressure. Then we change the pressure and find the new volume and change the pressure again and find the new volume. We're going to get a graph that looks like this. So if we measure pressure versus volume, or volume versus pressure, which is how I set it up here, we get a curved line. But if we measure the volume versus the inverse of the pressure, now we get this nice, beautiful linear line that goes through the origin at exactly 0, 0. So at 0 volume, we'd have 0 inverse pressure. Now between these two plots, really this top one is useless. That doesn't give us anything useful. This bottom one, however, has a constant slope situation. And that's going to be really key to the mathematics that we end up setting with this. So the top situation, we had a changing slope situation. That's not very useful to us. But the bottom relationship, volume versus inverse pressure, that gives us a linear relationship that hits the axes at 0, 0. And that's important. So since the slope of this line is constant, we say that V is directly proportional to 1 over P. Now in math class, and this is something that I don't think you've seen in math class, or seen much of it at least, that proportional to is this symbol right here. So all this means is V is proportional to 1 over P. This does not mean that V equals 1 over P. That's not what this says. This says that the volume is proportional to the inverse of the pressure. And remember that what that means is we're going to get a linear relationship that goes through the origin. Now mathematically, that statement becomes this. If volume is proportional to the inverse of pressure, then the volume over the inverse of pressure equals a K. Now, K universally in math class means a constant. So what we're talking about is a constant here. So the volume divided by the inverse pressure is always going to equal the same number. So therefore, the pressure times the volume. So if we resolve this expression and simplify it, that becomes this. The pressure times the volume of any gas equals a constant. Now, what does K actually represent? So what is K? Well, remember, what we're actually doing here is from this graph, the slope of that line. So what K actually represents is the slope of our graph line here. So remember, we said it's a constant slope. Well, that's actually what this K equals, is the slope of that line. Now, let me get rid of some of this garbage here. Now, earlier I said we say V is directly proportional to the inverse of the pressure. Well, another way to say that, because we rarely say this is directly proportional to the inverse of that, we simplify that to this expression. So another way to say this statement, which is not how we usually say or express that. It is true, but how we normally say this is V is inversely proportional to pressure. So if one variable is proportional to the inverse of the other, then we say it's inversely proportional. And that's a term, direct proportionality, inverse proportionality, you should have seen. At one time in math class, they went through this whole derivation of these ideas that we're looking at here. Nowadays, I don't think in your math class you get too much with graphing and proportionalities. So for some of you, that may be something totally new. So what we get is actually a relationship known as Boyle's law. Under constant temperature and number of moles, the pressure times the volume equals a K. Now, as long as we don't change the temperature or the number of moles, then this K is not going to change. So it is a constant. Now, the thing is, it's not a universal constant. So K in and of itself is meaningless because at every different temperature and every different number of moles, you would get a different value for K. So while it is a constant when T and the number of moles aren't changing, it's not really a universal constant. So we don't leave that K in the expression. What we really do is we recognize the fact that if N and T, because N is the number of moles, remain constant, then we're going to equal the same exact K. So under our initial conditions, which were in condition 1, so we call it P1 and V1, that equals K. Well, under a new pressure and volume, it's still going to equal K as long as we haven't changed the temperature or the number of moles. So what we really get is an expression that looks like this, which should be familiar from last year. Boyle's law mathematically is P1 V1 equals P2 V2. And that's our mathematical expression of Boyle's law. Now, the volume of a fixed quantity of gas at constant temperature and pressure then is inversely proportional to the pressure, or constant temperature and number of moles would be inversely proportional to the pressure. So that is the word statement of this mathematical expression. So this is Boyle's law in words, and this is Boyle's law in math. Next law is Charles' law. This is also the one you looked at first or second last year. The volume of a fixed amount of gas at constant pressure is directly proportional to the Kelvin temperature. Now you'll notice in the diagram over here, this is volume versus temperature, and it is linear. But notice we didn't hit 0, 0, which would be right there. That's because we're in Celsius. So we're off by, it looks like to be here, 273 degrees. That should sound familiar. That means we need to go to Kelvin temperature. That's why we have as an expression the volume of a fixed gas at constant pressure is directly proportional to its Kelvin temperature. Now, in this particular case, that would mean V over T equals our constant, which is, remember, the slope of this line. So the volume over the temperature would equal a constant. So a plot of V versus T, that's going to give us a straight line. And if it's Kelvin temperature versus volume, then it's going to intersect our axes, our origin 0, 0. Now, in terms of what Charles' law looks like, follow the same exact idea we did with Boyle's law. If V over T equals K, then V1 over T1 is going to equal V2 over T2. And remember, temperature must be in Kelvin. That's really important with this law. So that would be Charles' law. That's an inverse, Boyle's law would be an inverse proportionality. Charles' law, an example of a direct proportionality. When volume went up, temperature went up by a like amount. So when you have a directly proportional situation, that means one variable versus another is linear. When we had an inverse proportionality, that was when one variable is proportional to the inverse of the other. So remember, we fundamentally have two different types of situations here. So if you graph the two variables and you don't get a straight line, but you get a straight line when you graph one variable versus the inverse of the other, you know it's an inverse proportionality, and it's going to fundamentally look like Boyle's law. If the two variables give you a linear relationship themselves, you know it's a direct proportionality, and the law is going to look similar to Charles' law did. Now, Avogadro's law, another law that's mentioned here. This is one you may not have gotten into too much in pre-AP chemistry. The volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So fundamentally what that means is volume would equal K times N. Because remember, if it's a direct proportionality, one over the other equals our constant. So if V over N equals K, then that would mean V1 over N1 equals V2 over N2. Now this is a relationship we could have and maybe even mentioned last year. We just didn't really give it a name or a law. So this is actually a relationship that was looked at by the Italian chemist Avogadro, who Avogadro's number was named after. So this is another expression, but this is a new one. So what this really started with was the fact that it was a direct proportionality. And as a direct proportionality, that would be true. And that means it's going to look like Charles' law, which is also a direct proportionality. Now, Avogadro's law can be used in gas stoichiometry problems because what this really says, if we rearrange it, is the ratio of the volumes is going to equal the ratio of the moles. So if we knew the volume of one gas and we know what the mole ratio is from the balanced equation, we could actually use that to determine the volume of the other gas. So really an application of this is the volume ratio of gases equals the mole ratios of gases as long as we're at constant temperature and pressure. So the mole ratio is also the volume ratio. And remember, mole ratio is what we use in stoichiometry problems. So this allows us to do stoichiometry problems with volumes, which is something you'll be looking at eventually here. Now, other gas laws. Gay-Lussac's law looks at the direct relationship between pressure and Kelvin temperature. And since it's a direct proportionality, notice it looks like Avogadro's and Charles. Now, the combined gas law, we usually don't say this in words. We usually just write the expression for this. But in words, this would be the product of pressure and volume is directly proportional to the Kelvin temperature. And that math or that word expression would be expressed this way mathematically. So what we really have here are a variety of tools. If we have pressures and volumes, we can solve the equation using Boyle's law. If we have volumes and temperatures, we can solve using Charles' law. If we have volumes and number of moles, we can solve using Avogadro's. If we have pressure and temperature, we can solve using Gay-Lussac's. And if we have pressure, volume, and temperature situations, we can solve using the combined gas law. Most of these you did calculations with last year. The only new one here is Avogadro's law. Now, section 10.4 gets into the ideal gas law. So far we've seen that volume was directly proportional to inverse pressure, volume is directly proportional to temperature, and volume was directly proportional to the number of moles. So we have Boyle's, Charles, and Avogadro's law expressed here, and these all deal with volumes. Well, if we combine them, we would see that volume is going to be directly proportional to the product of N and T over P. Well, that means we can rewrite this expression to look like this, because remember, direct proportionality means they vary by a constant. In this particular case, since we have all four vast variables, the constant we're going to get is a universal constant, and we're not going to call it A, we're going to call it R. So once we turn this into a constant, we go from a sign that looks like that to a sign that looks like that. So we go, once we include the proportionality constant, then we go from proportional to an equal sign. So volume would equal NT over P times R. And if we rearrange that, we get something very, very familiar to last year. PervNerd, PV equals nRT. So this is our relationship between pressure, volume, the number of moles, and temperature. So if we have a situation where all of them are varying, we could use this expression to solve it. And since R is a universal constant, we can actually look at a real number here. We don't just get rid of that constant, it stays in our expression. So in order to do calculations, you have to have some specific units because R has to be expressed in specific units. So our units of R are really going to tie us down to what we're doing with pressures, volumes, and temperatures, and number of moles. So first pressure, well, it could be kilopascals, atmospheres, or millimeter mercury. Volume could be liters, or it could be meters cubed. Sometimes you will see meters cubed, but that's a very, very, very rare. Typically, with volumes, we're going to be talking about liters and milliliters. N stands for the number of moles. So if they give us the mass, we have to use the molar mass to convert to the number of moles. So that's a common problem that you have to solve for. So anytime you see grams, remember, convert it to moles for this chapter. RT is going to be temperature, and that's always Kelvin. So what we have here is a situation where we're typically in volume in liters. Number of moles would be moles, and our temperature would be Kelvin. The only one that really varies is what we've got here for pressure. So since pressure ends up being expressed in different ways, it would be convenient if we had different R's to handle the different pressures. Well, we do. R is the ideal gas constant, and it's really tied to what kind of pressure unit we want. It's 8.314 if we're in liter, kilopascal, moles, and Kelvin. So this is the kilopascal expression for R. And if we're in atmospheres, it's 0.08206. And if we're in millimeters of mercury, it's 62.36. All of these are equivalent to each other. So if you take any one of these numbers and do a conversion from kilopascals to atmospheres or atmospheres to millis of mercury, you'll see that they're all equal each other. So every one of these is a value of R. Which one do you use? It depends on which pressure we are in. So your pressure unit is going to determine your R unit in a problem. So rather than always converting pressures to a common unit, just use a different value for R. Now, all the other gas laws can actually be derived from the ideal gas law, and this is something you should have looked at last year. So remember, PV equals nRT, well, the universal constant here is R. So if we solve that for R, what we end up with is an expression that looks like this. PV over NT is going to equal R. And remember, this is a universal constant. So no matter what our pressure, volume, temperature, number of volts conditions, it's going to always equal R. So if we really wanted to, if we looked at ones and twos, we would have P1 V1 over N1 T1 equals P2 V2 over N2 T2. And we can derive any of our equations from these. If N and T are constant, that means these two would cancel and we'd be left with P1 V1 equals P2 over V2. If P and N were constant, they weren't changing, then they would cancel out and you'd be left with V1 over T1 equals V2 over T2. So every single gas law that we looked at earlier actually can be derived from the ideal gas law. So perv nerd, PV equals nRT, most important law of them all, because all the rest can be derived from that. Now here's a typical ideal gas law problem. What is the volume of 14.2 grams of O2 at STP? Now, we've got PV equals nRT as our expression here. And in this particular case, we're solving for volume because it says what's the volume. So our equation is going to be nRT over P. Remember from last year, something that should have been driven home in the gases chapter was don't plug in your numbers. Solve for your variables first and then plug in your numbers once you've got your expression. Now, in order to plug in my numbers, I have to have things in proper units. Remember I had said earlier, whenever you see a mass, that means you've got to change it to the number of moles. So using our molar mass conversion here, we know how many moles of oxygen we have. And notice I've left it to extra significant digits here. So I can plug that into our PV equals nRT. And since our pressure was in kilopascals, because since it said STP, I could have used 1 ATM or 101.325 kilopascals or whatever. I just have to get the appropriate R value for it. Since I wrote this in kPa for my standard pressure, then that meant I had to go with the 8.31 for my R value. Standard temperature is 273.15, and we just calculated the number of moles, so we can plug in and calculate to 3 sig figs because of um, our original mass here was in 3 significant digits, so that will end up limiting us to 3. We get 9.95 liters. So the volume in this particular case would be 9.95 liters. Next, standard molar volume. Standard molar volume is actually a shortcut that can be used in certain types of gas problems to make things a little bit easier. Or you can use the straight old PV equals nRT and solve it that way as well. But this is often a shortcut. So solving for the volume of 1 mole at STP is going to give us 22.41. Last year, remember, this is 22.4. I'm just going to extra sig figs here. So the standard molar volume of a gas is 22.41 liters per mole. So we can actually use that as a shortcut if it ever says we have a gas at STP. This last problem, we had a gas at STP. So one way to do this would be to calculate our number of moles and then just do a quick dimensional analysis problem. So I solve for the number of moles, last problem. If we have 22.41 liters for every mole, this should be a quick, easy way to solve the last problem. So remember, this is really a shortcut to the last problem. So if you ever see STP, think 22.4 liters per mole. Now, you can use 22.4. That just limits you to 3 sig figs. Since our last mole amount was going to be limited to 3 sig figs, I went to 4. It's not really that big of a deal. So if you use the same number you did last year, 22.4, that's perfectly acceptable. I was just going to 1 extra significant digit here. But this is a shortcut way of doing the last problem. So if you ever see you're at STP, ask yourself, Can I use the standard molar volume as a shortcut? And that ends.